Okay, so I want to thank the organizers, and I'm happy to be here since a long time. So I will present various results we obtained with Ego and many other people of his group. So our original title was for Skyrmions in resistive state of this electron quadrupling phase. But then Ego asked me to present a lot of other things, so let's try to see if I can fit everything for the duration of this talk. Okay, it's based on various papers, not all of them are listed here. Right, so I try to convey two take-home messages in this talk. First one is about superconducting state, especially S plus I state, but it's more generic than this. It's a consequence of what Electron taught, like multi-component physics, and that the superconducting states can naturally quite easily host a spontaneous magnetic field when the time reversal symmetry is broken. When you have, I don't know, like material inhomogeneities, and the reason is because this magnetic field that Ego introduced has two contributions. One which is the usual Meissner screening, and another one, the other component, which is really due to the multi-component nature of your other parameter, that is a composite emergent, say, magnetic field, and that cannot be fully screened under certain circumstances, that cannot be fully screened by the Meissner curves. And the other message, okay, I'm in front of, sorry. The other message is that I will try to derive an effective field theory to describe this electron quadrupling state, which is resistive, so it's above TC, but still has some remaining order, which relies on the broken time reversal symmetry. For this, I will derive a 4 Fermi parameter and give some expression of the spontaneous magnetic field and show that it has large topological content and various ways to get magnetic signatures even in this resistive phase. So, okay, let's skip part of the introduction. So, the framework here is we work with multi-component superconductors. Namely, I have a vector of complex scalar field, capital psi, with, I don't know, as many as components as you want. So it's vector in Cn. And in my notation, psi a, modulus, and phi a will be respectively modulus and phases of individual components. In this framework, you have, let's say, most generic Ginzburg-Landauer energy, which consists of magnetic field and then kinetic term of individual components, and some interacting potential with the parameter of the potential. Okay, it's first order, and parameter of the potential chosen so that, okay, its energy is real quantity. So you have some kind of symmetry relations between all your coefficients, which is not...
Excuse me, E, what is E?
Yes, E.
Is it twice electric charge? Or
yeah, here is a gauge coupling.
It's ordered as superconductor.
Yes, it's not electron charge. It's it could be like Cooper charge, but all generically it's a gauge coupling. Okay, you have your free energy. So Euler-Lagrange equation. You take variations of this free energy. It gives you two equations: variations with respect to the individual scalar field gives you a Ginzburg-Landauer equation for each of the scalars. And variations with respect to the vector potential gives you Ampère-Maxwell equation, where the current it's self-consistently determined by all the components here. in this framework, if I want to write more explicitly this Meissner current, I can decompose by a contribution, which is proportional to the vector potential, and another one which is proportional to the phase gradients. And here this rho square is total density. One important point that was raised at some point in the questions is that I can, and also in your talk, is that I can rewrite this by separating charge and neutral modes. Okay, I have charge modes, which magnetic field and Meissner currents, here in blue, have density modes, and I have neutral modes, which rely only in the difference in the gradient of relative phases between the condensates. So this is always possible, and all the interesting physics comes in this kind of rewriting. So, multi-component superconductors, there is huge variety of different kind of topological defects, fractional vortices that Eco mentioned, which consists simply in winding, phase winding in one of the condensates and not of the other. And all of these topological defects are associated with different maps and different kind of homotopy. They are classified by different kind of homotopy groups between those maps. You can have domain walls in case of discrete symmetry is broken, and you can have those CP2 skyrmions, but I will try to return to this, and you can have also options like knots. Let's skip the rest. So,
Can I ask?
yes.
So if you generically these two order parameters, psi1, psi2, they'll be coupled, Josephson coupled.
Yeah.
So really, there's only single U1. Let's say if you have two order parameters,
Okay.
there's really only a common U1, not two different U1s.
No, yes, sure. I mean, there is a single U1 gauge field, of course.
It's not U1 cross U1, it's really just U1, right?
Ah, yes, no. You mean like global for
Global,
the...
yeah, I'm talking about global.
Yes. So all this, so for the moment, I make no assumption on the potential. The potential can be U1 cross U1, U1 cross Z2, whatever you want. Okay, I have some symmetry. It can be SU2, why not? Or SU3 or whatever. So right now there is just no assumptions on the structure of the potential.
But physically, if you have like two bands, let's say, it would be termed like psi1 coupled to psi2.
Yes. Yes, of course. So for say physically relevant multi-band superconductors, you will have Josephson. Yes. So I will present some of them with Josephson terms. Yes.
Okay, thank you.
Okay, so just to return to this question of flux quantization, the concept that you have objects that carry flux fraction, it's somehow very simple. You define flux, and by expressing the vector potential in terms of Meissner current and the phase gradients, okay, here it's you use Stokes' theorem. And then you say, fine, I'm in superconducting phase, so the Meissner current decays exponentially. So far away from something, there will only remain this term of the phase gradients. And so if I say that only one component phase, then I will have something which do not amount to a single quantum of magnetic flux, but only a fraction. It doesn't say anything about whether it's stable, whether it's realized, but just formally you know you have objects that carry some fraction of flux. For the moment, nothing more. And all the interesting part is whether you are able to obtain such objects or not. Let's say. And yes, now about energetics. If I simply consider U1 cos U1, then, and I wonder about the energetic properties of an object which has just single winding. So, simplest object that carries fractional flux. Then you realize that it has logarithmically divergent energy. If you have Josephson term, it's even worse. It's linearly divergent, which makes them very difficult to observe. But you also realize that if you say that you have composite fractional vortices, or say the 1, 0 and the 0, 1, at total they have a single quantum, and you compute energy, and energy is finite. And this is why Igor was saying that these are the only finite energy topological excitations. They are not elementary one. Elementary one are the fractional vortices. They have infinite energy, but they are bound state, which carries integer flux as finite energy. That's what we do. So several ways to make a bound state of fractional vortices is either to make two of them sitting on top of each other, or just close together. And in this case, you will have, say, singular integer vortex or coreless integer vortex also. And in our terminology, coreless composite vortices, we call them Skyrmions, because they are associated with some particular topological charge. Okay. Now, let's jump to this story of time reversal symmetry broken states. So, there are many materials now which are known to have broken to phases which breaks spontaneously time reversal symmetry. They could be of different pairings, but let me put it this way. So I say that time reversal symmetry is broken if I say that psi 0 is my ground state, multi-component ground state. If I say that under time reversal operation, which is complex conjugation, if under this operation on the ground state, I end up with some state which is gauge inequivalent to the original state. By that I mean that I do time reversal operation if by any rotation I cannot return to the original state. And this I found a nice analogy for all of us that took like undergraduate classes and that used oscilloscopes. So suppose I have two signals on an oscilloscope, right? This, okay, I have two signals, and yeah. Oh, sorry, I missed something. Sorry. Yes, okay, and yes, sorry. So, for all practical purposes, this definition, to say that time reversal symmetry is broken, amounts to say that the relative phase between the different possible condensates, that this relative phase is neither 0 nor pi. So if you have 0 or pi, it's time reversal symmetric. Otherwise, time reversal symmetry is broken. And now I'm jumping back to my analogy with oscilloscopes. So suppose you have two signals, red and blue, red and white, which are in phase opposition. Now I take this picture, this is time, reverse time. Okay, reverse time, I have it like this. Okay, now I can tune the old signals to make them superimposed with the original. Right? Time reversal symmetric. This operation of shifting everything, it's more or less what I mean by global rotation of all the phases of the condensate. Now, suppose I have a phase shift which is, say, pi half. So it's neither 0 nor pi. Now, I take this signal, time reverse it, by any transformations trying to shift both signals simultaneously, I cannot superimpose on this. So this signal breaks, in this analogy, breaks the time reversal symmetry. So, you can think of the simplest two-component toy model, which will exhibit time reversal symmetry. So just gradient of phase and some potential term here, cosine of twice the phase. Here, if I look if M is real number, then the minimal energy state is that the relative phase would be plus or minus pi. It's neither 0 nor pi, so it breaks the time reversal symmetry. And clearly, the energy is invariant under sign change of the relative phase, but the ground state is not. So this discrete symmetry related to the time reversal symmetry, this discrete symmetry is broken by the ground state. Now, when you break a discrete symmetry, you allow for certain kind of topological defects, which are domainers that I represent here. And part of the question is, can these objects have magnetic signatures, and in particular for S plus IS states, which are interesting for us in the framework of ion-based superconductors. That's the second part of the talk. And the other one, yes, it's for this electron quadrupling phase. So I reproduced those phase diagrams from previous talks, and there is this interesting phase here, which is above superconducting critical temperature, but which still shows some order, namely that the time reversal symmetry is broken above the critical temperature. So, okay, forget about experimental evidence, it will be discussed after. Yes, but the physics here is that it's resistive, so U1 gauge symmetry is restored, but it breaks time reversal symmetry, so the discrete Z2 symmetry is broken. And yeah, I will try to give an effective description of this quadruplet state.
12 minutes. Is it? Yeah.
20 minutes, okay. I'll speed. There is this question of, yes, observability, spontaneous magnetic field. So, realization here is I consider a three-component model with various potential terms, and in particular, Josephson coupling terms between all the three components. Here, the setup is that you want that each of the individual Josephson term wants to have pi phase locking, and since none of them can be simultaneously satisfied, then there is some kind of frustration, and if you tune parameters, then you can end up in a phase where all relative phase between the condensate are neither 0 nor pi, and so they break time reversal symmetry. In this case, see a simple example would be this, but you have two inequivalent ground state configurations, and these are given by, if you go, say, counterclockwise here, go from blue, green, red, or red, green, blue. It's just pictorial representation. Right. So, now this means that in space I can have, by Kibble mechanism, if I go through phase transition, I know that different regions of space so of my material, can fall off into either of the ground states without knowing of each other. And so this means that when relaxing, I can have some configurations that interpolate the space between both ground states, and those are these domain walls. But in this plus IS superconductor, they are very difficult to observe because they do not carry any magnetic field. Contrary to, say, P plus IP models, here domain walls do not have magnetic field. So this makes these kind of objects difficult to observe. And so we want to try to figure out whether we can detect them through magnetic field. The reason why it's difficult to observe is that you can have various like individual currents through the domain walls, but all of them compensate exactly, and so you have zero magnetic field. But I realized that recently it's only true in one dimension, or in two dimensions with translation invariance. As long as you relax this, life is much more rich. By that I mean that if I put vortices on domain wall, I will see the domain wall. If I put thermal gradients, I will see the domain wall with magnetic field. Or if I have some material inhomogeneities, I can see domain walls. If I have pinning centers, I can see domain walls. And this relies on these modifications of the electrodynamics, especially on this multi-component, intercomponent. So, okay. So, yeah. So, here, suppose I drill two holes, and I have a straight domain wall through this. Okay? The hole, it's slightly roundish, which means that there the current cannot exactly compensate, and then you will see magnetic signatures on this hole. Simply because the intercomponent current cannot be completely compensated and cannot be completely screened by the Meissner current. Okay, that's another one. So now suppose here you see I have a domain wall, but I apply thermal gradients along the domain. Then again, so here I have say temperature which depends on space. And this will make the domain wall to spontaneously emit some magnetic field. And this is, yes, I did that yesterday. No, actually, day before yesterday, but it's not important. Now I have magnetic field, domain wall in this direction. And I say that I have random fluctuation, small random fluctuations of Tc. Then this will make the domain wall to emit spontaneously some magnetic fields. Or if I put pinning centers, which also amount to have some local variations of Tc, then domain wall will be pinned by the pinning centers. And then because of the local variations of the critical temperature, then it will, you will have uncompensated currents, and domain wall will emit magnetic field. So this is about domain wall, but it's also true for the ground state. I have my ground state which breaks time reversal symmetry, and I make small fluctuations of the parameter, the individual critical temperatures, and then I have spontaneous magnetic field inside the superconducting states. Or that's another one with linear gradients. And then also if I have some small pinning centers, then my time reversal symmetry broken state will also emit magnetic field. Okay.
So this is, before it was in a domain wall, this is in a bulk?
Yes, bulk. Yes, yes. This is bulk, this is bulk, this is bulk. Okay. So you will see that here the magnitude is different. Here, magnitude for bulk is 10 to the minus 4, 10 to the minus 3, while on the domain wall, it's at least an order of magnitude more. So it's easier to see. So you see here, yeah. Here you see there are some small fluctuations, but the domain wall, it's really order of magnitude larger.
Is the integrated magnetic field over a sphere zero?
It's local field. Local field, but yes, so if I integrate
You're talking only the z component.
yes.
Supposing I integrate over the sphere, is it zero?
If I integrate over the sphere. No, here it's just for 2 dimensions.
So you're taking a projection
Yes.
and then taking the z component of
Yes.
that.
Yes. No in-plane field. Okay. As we said, the reason is that for multi-component superconductors, you have like extra contributions of relative densities and relative phases in the current. And if you rewrite a magnetic field or electric field, you have extra contribution to the London electrodynamics.
But, excuse me. So in order to see this field, or generate this field, somehow the impurities have to act differently in the two components? Psi A, psi B coupled differently to the impurity?
It depends. So, the more it's different, the bigger is the signal.
But
So
suppose it's
if you
identical.
take the 2 impurities to be the same for both components, then you will have a smaller signal than if you take the 2 for different components. But you will still see signal. Yes.
Even if they couple the same?
Yes. Yes. For example, here it was the case for spinning centers. Spinning centers were exactly the same for both components.
And that's because somehow psi A and psi B don't compensate each other. The currents don't compensate.
Yes, but also they have, say, different personal length scales, and so they see the impurity differently. So one will see impurity, say, very small, and the other one very big, and so it will have different effect on how they recover. Okay. Yes. So the important part is this. So I see magnetic field, and magnetic field is contribution of Meissner screening and this composite emergent field. Now, if I look at both, they are different. So this composite field is almost an order of magnitude larger than the magnetic field which is observed. So it's partially screened. But as was mentioned for fractional vortices, length scales are different. They behave differently. It's not exponentially localized, and you can see this, like their shape and stretching is different from the magnetic field that you observe to this guy. Okay. How much time? 2 minutes. Okay. So, for this quadrupling state, okay, which is fluctuation induced, how do I get this model? So I take a 3-component model with quasi-classical theory, derive Ginzburg-Landau theory for 3-component, and here I choose a 3-band model where pairing is dominated by repulsion between the 3 bands, which means that I can nucleate only 2 mean field components, so I have to project back, and I just end up with a 2-component theory, okay, like this. It's not unimportant, with mixed gradients. So I eliminate mixed gradients by reparametrizing superconducting degrees of freedom with a square root matrix. And okay, I end up with a 2-component theory, with again vector potential expressed in charge and neutral modes, magnetic field expressed in charge and neutral modes, covariant derivative expressed charge, density, and neutral modes. So I just rewrite the whole theory in this framework with charge, neutral, and density. Now, for this effective model, I want to look at the quadrupling parameter. So I defined a kind of parameter, which I call M here, which is bilinear in the psi. But remember, psi are superconducting condensates, so there are already two fermions, right? So this M here consists of 4 fermions. I rewrite all my theory in terms of this quadrupling order parameter, and this is the phi-df term that Edgar was showing before. Here it's merely rewriting. And now I say in resistive state, so here it's just rewriting. And I say that in resistive state, so in resistive state, superconducting Meissner current is 0. Okay. Okay, it's a bit crude, but I don't have time to justify, but okay, we can argue this to be true. So I just kill the two total Meissner currents, and then the only leftover are these M fields. And this is Skyrmions model. Yeah. Slightly modified because there is some normalization, but it's more or less the same. And there is this spontaneous magnetic field. Okay. There is a topological invariant here. As if I define M divided by its norm, I have the maps between the 2 sphere and the 2 sphere, and the degree of this map is topologically invariant and is an integer, as long as these other parameters do not vanish. And I can relate the magnetic flux to this topological quantum number. So here it's interesting because even if I am in a phase where superconductivity is destroyed, so where restore the U1 symmetry, I still have a rule for quantization of magnetic field. Okay? Is it? Yeah. Okay. Sorry. Okay. And it has like a lot of stuff. It's in our paper with Egor, like a lot of objects with spontaneous magnetic fields, skyrmions. Egor wanted to talk about skyrmions in superconductors, but I don't have time, obviously. Okay. Yeah. Thank you.